Okay, so good afternoon, everyone. My name is Alfredo Escalante, and I'm going to present you for the fourth time the work we have been doing with the supervision of Manuel Sanjurjo and Pablo Giglino from Clepsydra. So the main goal of the project is the application of deep learning for optical navigation in various missions of solar system exploration. Last years we covered other targets, so today I will focus on the moon, but well, first a very brief introduction of the main goal of the investigation, which, as the title said, it's investigate if we can apply convolutional neural networks for optical relative navigation as a lightweight and robust solution. And this is because the classical methods that are used right now and for many years in navigation of interplanetary missions rely mostly in stereophotoclinometry, other algorithms as well, but what they have in common is that they are computationally expensive. So we cannot use them in CubeSats, for example, or commercial missions that are way under the budget compared to large space agencies missions, and also fail under adverse illumination conditions, which is mostly when the phase angle is close to zero, because you don't have shadows and the algorithms fail, or when the phase angle is very large and you have too many shadows. And that's why, for example, missions like Hera, it's only flying in phase angles between 20 and 70. And the main drawback of this is that you limit a lot the coverage of the missions, the operational limits. So that's very undesirable. So what we want to do is to train neural networks that are capable of learning the nonlinear transformation between the 2D space for a grayscale image or 3D if it's a color image to the 6D space of the pose vector. So 3 coordinates for the position, 3 Euler angles. And this way we would solve the previous issue with the current methods. Of course, to pull this off, we have to tackle some challenges. The first is that the CNN acts in general like a black box. So, of course, we have some tools to analyze what's happening inside, but it's not really human readable. So we have to perform a lot of testing to identify failure cases and scenarios and really validate the solution. Also, as it's very well known, machine learning algorithms require a large amount of data, a lot of data. And even if for some cases like the Earth or the Moon, we have a lot of data, still it's not enough to cover all the operational ranges. So that's one of the main challenges. And also we want to generalize the solution, which means that we want the neural network to work for orbiters, for descent trajectories, landers, different types of bodies. And in previous years, I covered some of the other targets. So we started the investigation with the comet case, and the asteroid, which are probably the easiest. It's mainly dominated by topography. Normally, you have all the limb of the target in the image, so that's it's very easy. Well, not very easy, but it's easier to estimate the position with that. And then we move to more complex bodies like the Earth, in which you have atmosphere effects, you have clouds, you have seasonal variations. You don't have the limb of the target, so that's way more complex. And that's what I presented last year, but not to repeat myself, because in the last month, actually, I've been busy with the thesis. So we did a side investigation of applying all this methodology to the moon, which is now very in the news with all these missions and the future human exploration, and has also very peculiar things which are not present in bodies, active bodies with atmosphere, which is that in the South Pole, for instance, you have very long shadows that extend hundreds of kilometers. And this applies also to other bodies like Mercury or the Galilean moons of Jupiter, for example. So these are some specific points that we have to address if we want to apply to all this wide range of celestial bodies that we have in the solar system. So a very brief history lesson on lunar missions. So this is, of course, very reduced. But we start with Apollo 15. That was the first mission of the Apollo program to be mostly dedicated to science. The previous ones were just to beat the Russians. This one had all these instruments in the service module. So the astronauts spent more days in the surface of the moon, and there was this poor guy that stayed here in orbit, and he was taking a lot of observations with X-ray, gamma ray, and of course a mapping camera. So it was probably the most detailed up to that date map that we had of the moon. And then 40 years after that, we have LRO, that has created global maps with an amazing resolution, about 5 centimeters per pixel in some areas, which to me is just amazing. And then we have many other missions, of course. And I think it's interesting to mention Smart One, that was a mission by ESA in the early 2000s. And this here illustrates these differences that I mentioned before about the phase angle. So the image on the left is the Hadley rail where the astronauts of Apollo 15 landed, right here, in 1971. And this is the same region with a completely different phase angle. This is close to 0. And this is an image captured by Smart One. So, of course, we have a lot of data, but the data that we have from, real data that we have from these missions, it's very constrained by the orbit and the characteristics of the mission. So with the solution that we propose, we want to fill the gap to cover all the possible ranges between these two, for example, and all the others. So the way we do this, it's by creating images. We don't have enough data. Okay, let's do it ourselves. And we do that by combining topography data, in this case from the ALERO mission. That's why I mentioned it before, that we have global maps at 118 meters per pixel. And at the South Pole, for example, where you can see these long shadows that I mentioned also before, we have resolution of just 5 meters, which is incredible. And then we combine this with albedo, again from ALERO, but from the camera. And the idea is that by combining both topography and albedo, we have a very accurate digital twin. And combining this to the neural network, as we will see in a minute, helps to this solution to work in phase angle close to 0, which is where the traditional methods fail. But in this case, the neural networks are capable of learning the albedo patterns, which is what the traditional methods can't do. And by combining these two, we fill this gap and cover also this operational regime. So what we wanted to do is we created this digital twin with ALERO data only. And with that, we generated synthetic images. And then we are going to test it with Apollo 15 images, which are 40 years older. So we started with taking the reconstructed orbit and pointing of the spacecraft. We reproduced the illumination conditions from ephemeris and rotation models of the moon and the sun position and so on. And also the instrument model of the mapping camera, which is this one here, which is basically the field of view and the image resolution. So with that, we can accurately reproduce all the images. And this is just for comparison of the real ones in the top row and the synthetic counterpart at the bottom row. And you can see that even with very large of nadir angles, well, maybe you can see here even the gamma ray boom of the spacecraft, the images fit very well and are very accurate when you compare the histograms, for instance. So we have all the images that will compose the training set, but then we apply also data augmentation to generalize the solution. As we mentioned at the beginning, was one of the main challenges. So most of these effects are introduced when rendering the images. So they are, once we generate the training set, they are fixed sort of. And these are mostly the orbit, so altitude and scale, the pointing of the camera, illumination conditions in terms of intensity and direction, Gaussian noise to model perturbations or just noise in the image, but in some cases even dust or venting from the spacecraft. And also we applied random small scales variation of the surface to account for defects or possible inaccuracies in the model that we're using for rendering. And then we also applied other effects during training. So this means that at every training epoch, they are randomly applied. And these are mostly the shear and zoom, these variations that you can note here. Then the pixel intensity histogram shift that I didn't have time to explain, but it's key to bridge the gap between synthetic and real images. And also the random cutout arrays, which are those random rectangles that block part of the image, which are used to model blockages, but also, for example, in the Earth case, when you have clouds over the terrain, for example. So that's for the images. Then for the neural network architecture, we are using what we call a two levels network. So we have one single high-level multi-class classification network that estimates the sector of the 3D space in which the image corresponds to. And we have tried different levels of discretization. And then based on the estimation of that network, the image is sent to one of a set of low-level regression networks. Each of them is trained only in one sector. So based on the workflow is the high-level classification chooses the network, the low-level network that will estimate position and Euler angles, which are the final goal of the network. So just some super short results with 16 sectors. So 4 latitudinal and 4 longitudinal divisions. with the classification we get with a very light architecture like MobileNet, almost 100% accuracy. And then testing the low-level regression networks, we needed a bigger model with more parameters, and we get less than 1 degree accuracy in the position with the most perturbed case. Of course, in reality, you have star trackers and you have other things that you can combine, and then you could get close to the 0 point something accuracy. Of course, based on this level of accuracy, we can probably increase the level of discretization to 32 or up to 64, as we did for the Comet case, for example, and then this would alleviate a lot also the accuracy in the low-level regression. But as I mentioned for the moon, it was more as a side investigation, and we didn't have time to develop fully everything. So then once we have the network trained just with synthetic images, we validated with the real ones that we take from the Arizona State Archive of the Apollo 15 mission. And we found out that we kept exactly the same level of accuracy with the real images that when we provided the synthetic counterpart to the neural network. Also, we have tested the execution of this in flight-proven hardware. With 8 gigabytes of RAM, ARM64 dual core, we get 12 frames per second, which is more than enough for a standard navigation filter, with just a 62% CPU usage. And the great thing of this, then tackling this computationally expensive thing of the current algorithms, is that this model is just 200 megabytes, all the high-level classification plus all the low-level networks. Also, we have tested this with a navigation filter, and the accuracy improves a lot, but again, in just 10 minutes, I don't really have time for everything. So some conclusions: we have validated the network with real images, with a mission which is 40 years old. So it actually fills the gap between these synthetic and real images for various scenarios, completely different operational regimes. Also, the proposed method is applicable to multiple types of celestial bodies. So we have tested it in comets, asteroids, moons, and larger moons, and planets with atmosphere and which are active in the end. And also, because the architecture is very lightweight, it allows us to train on ground even repeated times, and then upload it to the spacecraft, which is already flying somewhere, in a single ground pass, which is very convenient to retrain as we have more data, for example, in a new mission. Some achievements, I will run through it very quickly. We published 3 papers already. The last one, just probably it's the one worth reading if you are going to read one, because it contains all the implementation from the first 2, but more developments that allowed for improved accuracy, and we even implemented time-distributed networks to analyze sequences of images that also improve a lot the accuracy of the networks. And I think that's it. Here I put the QR codes of the papers in case you want to take a look, and I would be happy to take any questions.